Okay, exceptions in Haskell, beginner's guide. The format of this presentation is kind of a two-pronged attack. It's a book report. It's my sort of summation of an imprecise, a semantics for imprecise exceptions in Haskell, asynchronous exceptions in Haskell, and this other paper that Simon Marlowe wrote about. Another paper that Simon Marlowe wrote about an extensible hierarchy of types. So there's that. I'm going to give an overview of the control exception API, give you some ideas on how you can use it, and provide a little bit of show you the semantics for exceptions bolted on to Haskell that you encounter in GHC today. Okay, so as I mentioned, I'm going to explain the exception semantics in Haskell and GHC specifically. I'm going to show you how to use them in your program. Beginning Haskellers start with exceptions as values. And what I mean by that is we've got these types like maybe and either that we interact with that help us represent failure in the type system. So you're going to use something like lookup. You're going to have like a map with keys of type A and values of type B. You're going to define one of these things. You're going to look something up in it. And if you're successful, you're going to get back just string. And if you fail, then you've got this value that represents failure. Either type you're also familiar with. Either decode is a function in ASON. It's going to allow us to go from a value of type byte string to either string A, where A is a type that instantiates from JSON. So this is going to be a thing that's going to allow you to decode a byte string into some type. For instance, you call either decode, you apply either decode to some string with 1, 2, 3 in there, and you say try to decode this to a list of integers, and you're successful, so you get back the right constructor with list 1, 2, 3 is your value. You try to apply either decode to the same argument, but you try to you tell it to produce you a list of booleans, and you get left representing failure. So the notion of success and failure is encoded in these types. And then you do things like you use head, and you apply head to an empty list, and you see some weird crap in GHCI that says exception. You go, what? And then you divide 10 by 0, and you see something that says exception. You go, what? And then you try to read a file off the disk, and you give it some bogus path, and you see an exception, and you go, oh my God, I didn't even know Haskell had an exception system. I thought this notion of functional purity would mean I would never have to deal with these out-of-band, this way to signal failure in a sort of out-of-band way. Okay, so I was digging into the papers that ultimately resulted in the incarnation of exceptions that we see today in the language. And they provided some justifications for why exceptions as values isn't always like the way to go. One of the things they mentioned was code bloat. Let's say you've got these two functions, f of g, which are from string to maybe string. You'll notice here that if I want to combine their inner values, let's say using string concatenation, I have to do this like error propagation check and propagate, check and propagate. I can eliminate some of the boilerplate noise in my program by using the monad instance of maybe, but then I've just incurred this first this, then this. I've created a sequence when actually these two operations have nothing to do with each other, just the concatenation. So you can get rid of some of this stuff by using applicative, but if we had to write this code all the time, our lives might be kind of sad. Especially if you show this to somebody coming into the language fresh, I think there's a little bit of like a hurdle that they'd have to jump over conceptually. Okay, you also run into this issue with modularity, where you're attempting to compose functions that could fail with functions that cannot fail in the ways that that we're talking about here. For instance, summing. You got x plus y, and you got y div z. So we know that if you try to divide a number by 0, you're going to get a runtime exception. You're going to get a div by 0 error. So we say we demand safety, and we write our own function safediv that returns a value wrapped in one of these maybe types. So we say we do some pattern matching. We say if you give me a denominator 0, we're going to give you nothing, and if you give me something else, then I'm going to do the division. I'm going to wrap it up and adjust for you. But now you've got this issue where you want to compose something that returns a type something returns a value of type maybe int. With this other thing that just speaks with ints, you can introduce a little boilerplate here. Once again, you can go back to the world of like applicative, or you can lift the result of this x plus q, or sorry, of the you can lift this little guy here, the plus q, up into the sort of maybe context, but it's certainly a whole lot more code than that. And we wonder to ourselves, like, am I really going to be dividing by 0? Is it really worth the additional characters for this marginal benefit of safety? So the other thing that they talk about in Semantics for Imprecise Exceptions, which is a spectacular paper and really helped me understand like how this stuff works in GHC. They bring up the point that it becomes very easy to accidentally make your lazy Haskell program strict when the return types of your functions are these values, the return type, you're using these types that represent success and failure. So we know that Haskell is a lazy programming language. So I got this choice function that I wrote. It takes a Boolean, takes two integers or expressions that are reducible to integer. And depending on the value of the first argument, true or false, we're going to give you back the left or the right argument. So you give me a true, I'm going to give you x. I'm going to ignore the y. If you give me false, then I'm going to give you the y. This property allows us to do things like this, where I call choice with true. True means that I'm going to pass along the left side of this, so the x, and the right-hand side, which, if it were evaluated to normal, if it were to evaluate all the way down to normal form, would result in a runtime exception, but we don't actually do anything with it, so we can write code like this and have it not fail. So let's say, like, what do we do in a world in which, like, what do we do in this world in which, like, we write safe div instead of using our unsafe div? As I showed you here, choice composes easily with div. X div y is going to give you an expression of type integer. Y div z is going to give you an expression of type integer. So we do bar applied to true 1010. We get back 1. 5 div 0 is never actually evaluated. No big deal. Though we write safe div. Now you'll notice that in order to apply choice to two integers, we actually have to pattern match on the return value. We have to pattern match the constructor of these safe div calls. And what we've accidentally done here is made this program strict. So the same, choice of divs prime true 1010. This should only work on the left-hand side. But the fact that we're doing this pattern matching actually drives evaluation of that expression on the right-hand side, and we get a divide by 0. So this is not like an insurmountable problem, like just don't do this, but it becomes easy to make little mistakes that have cascading effects through your system. The other thing is this notion of asynchronous exceptions, which is a concept I'd never really thought about before. This great quote from the paper: asynchronous exceptions by their nature have nothing to do with the value of the unfortunate expression that happens to be under evaluation when the external event occurs. Things that would be represented in Haskell by external events are like stack overflows, or the user hits Control C or something like that. Let's say I've got a function that just adds two integers together. How would the type of that function represent the potential for a stack overflow? Like, all functions would need to be able to represent all of these different types of errors. So they've made some trade-offs here. Trade-off is a word that Phil mentioned to me when I was whining about this exception stuff. And he's got a point. Like, you traded a little bit of safety for concision. You can compose addition and division, and you don't necessarily need to wear the safety belt and do all of the unwrapping of that resultant maybe, or that value of type maybe. Safety for transformations, writing that code in a monadic style implies a do this and then that, which limits our ability to do these types of transformations that you're going to get in other parts of your program that are enabled by the fact that evaluation order is unspecified. For instance, with addition or something like that. Safety for modularity, you can compose addition with division. Safety for laziness, you don't necessarily need to worry all the time that you have accidentally introduced strictness into your program. And then once again, there's no story for representing asynchronous exceptions if you're in this world of exceptions as values, like maybe and either. If you don't buy any of this, that's totally fine, because if you're going to use any of these libraries, you're going to have to deal with thrown exceptions anyways. So too bad if you're like me and you say, synchronous exceptions, they totally suck. I don't believe that they should exist. Too bad. You're going to have to, if you're going to write code that relies on these things, you're going to have to deal with it anyways. So it behoove you to like figure out how they work. That's how I sleep at night anyways, telling myself that. Okay, so two flavors of exceptions. I touched on this. Synchronous exceptions and asynchronous exceptions. Synchronous exceptions are the class of exceptions that you're probably used to dealing with in other programming languages. You write the try-catch block around it, you evaluate some statements, and some exception pops out, you catch it. It's let's say a way of signaling failure a way of signaling an out-of-band failure. Giving some examples of that: reading a file, passing it a bogus directory, passing it a bogus path, you're going to get an IO error. Synchronous exception: 20 divided by 0, you're going to give div by 0, have an empty list, etc., etc., etc. The paper goes on to say that the denotation or the meaning of an expression will tell you whether or not the expression will raise a synchronous exception. So the potential for raising an exception you're going to see if you actually do if you actually like write down the denotation of the expression. And you may be thinking to yourself like, well, what the hell does that mean? And I will show you using my awesome math skills. So I wrote this function bitflip that takes an integer and returns an integer to illustrate this notion that the synchronous exception is actually part of the meaning of an expression. So you give it a 0, it gives you back a 1, you give it a 1, it gives you a 0, you give it anything else, it's going to invoke the error function, which delegates down to throw. Something to think about before I go on to the next slide. In Haskell, and I haven't really thought exactly how to explain this, well, we signal failure by creating exceptional values. The paper distinguishes between normal values and exceptional values. It's important to note that these exceptional values don't actually impact your program unless they're evaluated, right? So you can think about this as like there are bugs all over your program today, but unless you hit that path, it doesn't actually matter. And Haskell takes it a step further. Unless you actually evaluate the expression down to the point in which you're going to hit this exceptional value, it doesn't necessarily it's not going to impact things. The other thing to think about is that exception values are infectious in pure code, and I'll show you. We'll walk through the denotational semantics of a Haskell function. I'll show you what that looks like. So I don't know how to use LaTeX, so I had to like write this down by hand. Sorry. But I was like, man, I'm so mathematical. I felt like a scientist for a moment there. Okay, so this notation is just stolen from an imprecise, or a semantics for imprecise exceptions in Haskell. My bitflip function, I'm just going to walk you through it. So bitflip function applied to an expression E in some environment P. If that E is not an exceptional value, so I've got this like OK to represent a normal value, I'm going to call bitflip prime, which is like an auxiliary function that actually does the stuff that you saw in my Haskell program. If I get 1, then I'm going to return 0. If I get 0, then I'm going to return 1. Otherwise, I'm going to return an exceptional value with some information about the nature of the failure. And you can see, I mean, you don't have to do that. You don't have to write that stuff out to see that this potential for raising this synchronous exception is actually part of the definition of the program. We just look here. And the point I'm trying to make is that like if you dig into any Haskell function and you see throw or throw IO, then its meaning includes this potential for raising one of these synchronous exceptions. Pattern match errors also fall into that. So there's like an implicit, like code path that you could follow that would result in non-termination, and that would be represented in the denotation of that function, even if you don't see it in your actual Haskell program, right? Like I could omit this right here, and you'd still see that if you were to write out bitflip's denotation. I mentioned that these values are infectious. I walked through the happy path, or rather the path that bitflip sort of like expressed in its code here, right? 0, 1, 1, 0, or an error. But I mentioned this infectious aspect. So what I was saying here is, on the right-hand side, it says if OK value, like if this E is an OK value, then go to bitflip prime and do all this crap that I wrote. Otherwise, return an exceptional value. So if bitflip is given an exceptional value, don't do this. Just result, its meaning is actually the original exceptional value. I didn't define this S function here, so you can ignore it. But essentially, what that's going to do is it's going to give you back the set of exceptions, the set of potential exceptions in it's going to give you back the set of potential exceptions contained in that expression E. Anyways, so I mentioned before, if you dig down into these things, you're going to see throw, you're going to see throw IO, or you're going to see pattern match. You're going to find a pattern match error. Okay, so that's the recap of synchronous exceptions. They should seem somewhat familiar to you, things like throw you've encountered in other programming languages. And the thing I want to drive home is that the function's definition will tell you if it will throw a synchronous exception or not, which contrasts with the asynchronous exceptions that you will encounter in a very different sort of way. Okay, so asynchronous exceptions in Haskell, another excellent paper, explains a sort of justification for the implementation of asynchronous exceptions that you find in the language today, and specifically in GHC. They mention that asynchronous exceptions are raised as a result of some external event. Examples of that, these are the constructors for the async exception type in control.exception: stack overflow, heap overthrow, thread killed, user interrupt, some thread throwing an exception of any type that instantiates exception to some other thread. These are all things that raise asynchronous exceptions, and they're not going to be like they're not going to be part of the semantics of your program, because someone could the stack could overflow at any point, reducing any one of these expressions that ultimately compose together to make your function or whatever. And once again, so they're not part of the semantics of the expression. I've got some contrived example that shows this. So I got this next positive int function that takes an integer and returns an integer. You don't have to write down you don't have to do the denotation for this function to see that its meaning does not include non-termination, right? Like it is not a partial function. So its behavior, you apply it to some number and it'll count up to that number. So next positive int 10,000 is going to give you 10,001. So we can make this thing fail if we configure GHCI with an arbitrarily small stack size, right? Let's give you 100K. Let's give your stack 100K. Load this file up, run this thing on, let's say, apply it to 200,000. You'll see a stack overflow. So this is like this notion that some external event is like signaling to your code to explode. Nothing about this code tells you that it could explode, right? It is not a partial function. The other thing, evaluation of any expression can yield an asynchronous exception. And I'm sort of beating this horse to death here, but I'll give you another example using throw2. So you can imagine this is all part of the same file. I've got my main function. This main function is going to fork. It's going to create a new IO computation to run in some other thread. It's going to run my sleepy function, which is going to sleep. It's going to print some stuff to standard out. This guy here is going to sleep for 1 second. The guy on the right is going to sleep for 2 seconds. Main thread's going to wake up and it's going to throw an exception to the forked thread. So thread delay 2 seconds is actually, from the purposes of our program, is the expression that's being evaluated, right? When this asynchronous exception is thrown to this forked thread. So we can replace, we can just do in our heads, we can replace that expression that was being evaluated with the exception thrown from this other thread, and we never actually make it to the woke up. So my point I was trying to drive home here is that thread delay says nothing about exceptions. Any one of these expressions evaluating any one of those expressions could result in an asynchronous exception. Blowing the stack, someone kills the thread, et cetera, et cetera.
One question. On the last code, does the behavior of this have anything to do with the fact that it's in an IO monad, or is it just whatever expression just happened? Do you understand the question?
I don't think I fully understand the question, but
so like does it make it synchronous with what's happening in the IO on the other thread, or does it just, it could be executing any computation? And
any expression, like pure code, whatever, it doesn't matter. Any expression, evaluating any expression could result in an asynchronous exception. It happens to be the case that, let's say, well, I've got all in pure code on the right-hand side, but I could be adding like x plus 1 plus 2 plus 3 plus 4, and that could be the thing that's happening, like when someone throws 2, and that could be replaced with a asynchronous exception. Yeah?
Sorry, so with asynchronous exceptions, can you catch them, or
yes.
Are you going to, okay.
In fact, I am going to talk about exactly that.
Wonderful.
Okay, represent things like user interrupts, resource exhaustion, blah, blah, blah. They can be raised anywhere in your program. Pure code, impure code. Okay, so that's a lot of background. How do you use this stuff? How do you actually write a computer program that deals with these errors, throws these errors, et cetera, et cetera? How do you signal these out-of-band failures yourself, and how do you handle the case in which like a library is trying to signal to you that something has gone dramatically wrong? Okay, so I keep mentioning that these papers these papers that I keep talking about have proposed things that have ended up in GHC. Haskell 98 and Haskell 2010 did have a notion of exceptions, but it was a little different than what you see today. You got a simple exception handling system in the IO monad. So you could do things like create your own IO error, and you could throw an IO error in the IO monad, and you could catch IO errors in the IO monad. But you couldn't do things like raise exceptions in pure code. You couldn't create your own. Exceptions. You could only use this IO error thing. And there was no way of dealing with asynchronous exceptions. These 3 papers ultimately resulted in many of the features that you're seeing in GHC today. I highly recommend. I got some links to it at the end of the talk. I highly recommend you go read about this stuff. They explain it in much greater detail than I do. So the API of today, control exception exports a few things that are important to you if like you need to deal with exceptions in your program. It exports the exception type class, which, as you can see, is the type class that you're going to be working with the most if you're going to be catching and throwing exceptions of your own. It also exports some exception and a relatively shallow but useful hierarchy of exception types, which you can extend with your own stuff. But some exception is the root of this, this structure of exceptions. So I mentioned those guys. I'm going to walk you through some of these low-level functions. It exports a bajillion functions that build on these things, but these are about as low as you can go. So throw does what you would expect. Given a value of a type that instantiates exception, it will plug in anywhere where you can use a value of type A, which is kind of bizarre, right, if you think about that. I'll get into that in a second. Throw IO, same story, only this is for throwing an exception in the IO monad, or producing a computation that when run will give you one of those things. Catch does what you would expect. You give it an IO computation that when run produces an A, you give it an exception handler, it'll give you back a new IO computation with that exception handler installed. And then mask, which helps you in dealing with the delivery of asynchronous exceptions. So as I mentioned before, dealing with asynchronous exceptions, these things can show up anywhere in your code. You might end up in this scenario in which let's say you've acquired some resource from a resource pool. Now you're computing pi to 10,000 decimal points. Someone delivers an asynchronous exception to you. You don't want to die. You want to release that scarce resource that you've acquired before you actually die, and mask will help you do that. Okay, so first thing, throw can be used to raise an instance of the exception type class in any part of your program. The words that I'm using are a little wishy-washy. It can actually be used to create an exceptional value somewhere in your program. And I mentioned this distinction between normal values and exceptional values. So you can see that this absolutely type checks 42 plus throw error call. Oh my God. right? So I said here that you produce a value of type A, which is kind of foreign looking, right? To get an intuition as to sort of like how that may work, imagine this function. The type of this function is integer to integer. Well, this is me actually like telling GHC that it's integer to integer, but this makes sense, right? Like, given an integer, I will produce you an integer. If you apply that function to some integer, now you've got an expression of type integer. This is an expression of type integer to integer. Going a little further, this is an expression of type integer to integer. If I fully apply this thing, or sorry, if I apply div to the remaining to x, sorry, if I give div like the integer that it's waiting for, now I have an expression of type integer. That totally makes sense. So why wouldn't it make sense that this too is an expression of type integer? There's this exceptional value waiting in there to be evaluated, but from a type perspective, the type of that expression is still integer. Okay, so brain teaser, for those of you that may or may not have been paying attention. Given the function f in my little program here, when I evaluate, or sorry, when I apply f to 10, and I print that out, this thing is fully applied, this function is fully applied. Which exception will be observed? Any guesses?
Think about the cardinality of the...
I cheated because I know the answer. Hey, yeah, what's up?
So GHC says plus is infix L, so my guess would be the left one.
But does it depend on the implementation, not depending on the evaluation?
All excellent guesses.
I think you can't tell from that statement. You can only tell if you respect the implementation of plus.
Let's check it out. Let's run it in my fantasy console. So I'm not as brave as Phil. I do not do this stuff live. I'd be like shaking at the keyboard. So this is the same program here on the left-hand side. And this is actual output from my computer program. So I'm compiling my little program, and I've disabled all compiler optimizations. And then I run that thing, and I get divide by 0. And I look at it, and I'm like, okay, yeah, that makes sense. It's like on the left, and like other programming languages I've used, like that's what they do, you know? I think JavaScript, I actually have no idea what JavaScript would do, and I wrote that language for like 10 years. But anyways, like I looked at that, and I was like, yeah, that totally makes sense. So then I compiled the exact same source code with optimizations dialed to 11, and I ran it, and I saw irk, and I'm like, oh my gosh, like what does this mean? So I go back to the paper, and I find this. And I was like, oh, yeah, this totally makes sense. Actually, so I sat there and I looked at this. I went into like the denotational semantics like dojo, and I actually came out with an understanding of what's going on here. So I'll walk you through it. So this is the denotation of addition in Haskell with exceptions. So these two things are primitives. This is like addition of E1 and E2 in some environment P. If neither E1 nor E2 contain an exceptional value, if rather they are like normal values, then go ahead and add these two things together using auxiliary function whatever that thing is, which is defined down here and looks kind of sort of familiar. But if either one of those two E's is an exceptional value, union the exceptional values of one with the exceptional values of the other. And that's kind of interesting, like when you go back to this actual code example, the meaning of f applied to 10 is actually the union of that exception and that exception. Practically speaking, you're going to get one of these errors, but only when you observe it in the IO monad. And that's an important distinction to make. Like the semantics of the expression is actually the union of both exceptions, but it's up to the compiler to figure out exactly which one it wants to do, and you can only observe it in IO anyways. So, you know, there's that. Expression evaluation order is unspecified in Haskell. That allows you to do a variety of things. One of those things is the compiler can, let's say, memoize certain parts of your program. You might be able to compute different parts of your program in parallel, blah, blah, blah. And you get some of those properties, I guess, if you can think about them independently and in order independent manner. As I mentioned before, and as I demonstrated in my Fantasyland REPL, the compiler actually will make that choice depending on whatever. Like it consults some external oracle, I think is the term used in the paper, somewhat flippantly, but compiler optimization flag, or it like checks the NASDAQ 500 or whatever. But you're going to get, you might get different exceptions observed in the I/O monad, and exactly why that happens is somewhat opaque to you. Okay, so exception propagation and I/O. This stuff is like a little more in the sane world. I could understand this. Exceptions, when they bubble all the way up to I/O, will short sequence the sequence of monadic binds. So you can imagine like F bind throw IOE will just result, pardon me, in F bind throw IOE. G and H, we don't get that far. This thing short circuits unless there's some exception handler installed. And given that most of your computer programs are just a series of like these things, that approximates like blowing the stack in Haskell. Haskell's particular flavor of blowing the stack. Catch function, as you would expect, allows you to install an exception handler. Given an I/O computation that when run produces an A, you give it a function from an exception to another I/O computation. You get back this I/O computation with that exception handler installed. You are familiar with read file. Let's say you give it some bogus path. That's bad. It'll run your exception handler, and it'll give you back a value of type IO, you know, whatever you parameterize it with. So in this case, when my exception is encountered, if it is encountered, because I gave it some bad path, I'm going to write something to standard out the string representation of that IO exception that was raised as a result of running that. Running the value that I got out of fully evaluating that expression right there. The transition rules with catch are also not totally surprising. Throw IOE, bound F will give you throw IOE, catch, my-cool handler will give you my-cool handler E, and so on and so forth. If you don't have an error and you install an exception handler, your exception handler is not going to be used. Other functions of interest, which I'm not going to get into, but are going to be useful for you and are somewhat low level, so are worth pointing out if you're going to be managing exceptions in Haskell. Evaluate, which given a value of type A, or some expression whose meaning is some expression of type A, will give you back an I/O computation that when run will evaluate that expression down to weak head normal form. Yes, that is correct. So this is useful if you have some pure computation that you may expect to like blow up with a synchronous error, and you want to like run that thing in the I/O monad, I guess, as its type implies.
Can I ask you to remind me? I should know what weak head normal form is, but I don't know.
I actually don't have like a precise explanation for what weak head normal form is. I think down to the first constructor, like evaluating down to the first constructor, but that's probably technically incorrect. Would anyone else like to pitch in? The question was like, what does weak head normal form mean? Oh, validation. Yeah, all right, so I guess I was right. Catches, unlike catch, allows you to install exception handlers for very specific exception types. So catch is a little coarse grain. Catches, you provide some enumeration of handlers that will work on different types of exceptions. Try, which will give an I/O computation that when run will produce an A, will give you back an I/O computation that when run will produce a left if running that I/O computation resulted in an exception or a value of type A, of right A, if not. And then finally, which does, what finally does in other programming languages. But this is all built with functions. The final thing I'm going to talk about is the mask function. I mentioned working around this notion of like asynchronous delivery of an exception to some code that's like not expecting it. You get this tool mask that allows you to work around that program. Specifically, I found it useful for preventing leaked resources. So going back to my like two slide thing, or two pane thing, you'd imagine these are all in the same file. I've got my main. My main is going to it's going to fork off a new thread and it's going to run this worker function. This worker function is expecting a connection. It's expecting a function that, like, when given a connection, will produce a computation in the I/O monad that, when run, produces an A, and it gives you back this I/O computation that, when run, produces an A. Walked through that. So it also starts this. It forks this thread and it gives it 5 nanoseconds to run. So it's not a long time. But the first time this thing runs, it just cruises through. It leases a connection from a connection pool in 1 nanosecond. And then it does some work in 1 nanosecond, binds that to result. It releases the connection in 1 more nanosecond, then it returns the result. And by gum, we complete in time. We can bind the resultant value to this name val. And then we print out its string representation to standard out. And the world is sane. We acquire some scarce resource, we do some work with it, then we release it, we're all good. But what happens if we don't get that work done in 5 milliseconds? Maybe work to do takes, 5 nanoseconds. Maybe work to do takes a year or something like that. Start cruising through this program again, we lease a connection from the pool, we start doing some work, and then we time out. The way this is implemented is we throw an asynchronous exception to this forked thread, signaling that it's like lowercase t, time to go home. And then this thing can be replaced with the exception that we threw, and we leak this resource here. So that's bad, right? Like, it may be the case that, like, leaking these resources, there's nothing else that cleans up after them, and then our program sort of drifts to the point where there's no more connections to lease from the pool, and we're sad. And the phone rings at 4 o'clock in the morning on Thanksgiving. So we've got this function mask. I won't explain that type because I can't, but I will show you how to use it. Same function over here. Main does this this whole timeout song and dance where it forks off this worker, but now I've got mask in play. So I call my mask function, and what I'm going to do here, I'm not going to walk you through all of it, but spiritually what's happening here is that this code is all asynchronous exception proof. And there are some exceptions to that, namely around interruptible actions, but I'm not going to get into that in this talk. But you can basically think of like this mask sort of preventing asynchronous exceptions from being delivered into any one of these expressions, or being delivered in the place of us evaluating any one of these other expressions. We have to tell it exactly where asynchronous exceptions can be delivered. So what happens then is that the result of evaluating this expression is an I/O computation that will essentially collect all of the asynchronous exceptions that would have otherwise been raised, like in here and in here, or whatever, which allows us to catch them with the regular catch function that we're given in control exception.
So umask is like saying, here's the one exception to this masked code. Here's where exceptions can go.
I think of it as unmasking. Like, I think of it as like I've got this sieve that I've just installed, and like asynchronous exceptions are bouncing off the rim of the sieve, and this is like the very bottom of the sieve. We're saying like if you collect anything, like you can deliver it here, only here. Does that make sense? Ish?
Ish.
Yes, Phil.
So ordinarily, if you didn't have the mask, would catch asynchronous things or only synchronous things?
Catch would catch a synchronous thing if work to do was the expression that was being evaluated when, if the question was like, if I were not using masked, like, and someone threw an asynchronous exception here, could I use catch? The answer to the question is yes. Like, for instance, I had an example earlier where I was like sleeping. You saw that when I was sleeping on the right-hand side, and I timed out that sleeping thread on the left-hand side. The expression that was actually replaced with the asynchronously thrown exception, you could have wrapped a catch around that. You didn't actually have to use mask. So if you could approximate what mask is doing, I guess, by wrapping every single expression in your program in a catch. I guess it would allow you to do something similar. Is that?
Mask only waits on, only prevents asynchronous exceptions from being observed, right? Not synchronous. So catch is both, but mask is only asynchronous. Right?
That's a good question. How would a synchronous exception interact with mask? How could it? Are you saying like if you were to raise a synchronous exception inside the body of mask, does mask like catch it and then put it like in here? I don't actually know. I'm not sure how that works. Does his question make sense? Yeah, I don't know. I'm not sure.
If a synchronous exception is raised in work to do, I would expect that to also be caught though.
Yeah, I would as well.
Yeah.
Yep, I would as well.
So the use case you were describing was that in this case now, we would still have a chance to release our resources even if the exception happened.
Yeah, exactly. Like, let's say that this little guy timed out. This guy signaled to this little guy that it was time to be done. The asynchronous exception would be, we'd unmask. Here, my laser pointer doesn't work on screen. Well, anyways, the masking would, I would unmask at this point. The asynchronously delivered exception would be raised here. My catch, the handler that I'd installed using catch would run, and then I'd have a chance to release and rethrow the error. So I wouldn't actually hit here and here. It wouldn't matter. I'd rethrow the error and my program would terminate. But at least I could release that. I could release. Yeah, what's up, Devin?
Sorry, one point to Phil's question. If unmask is allowed to be called multiple times, that would suggest that it would not be the single point of entry. So like any exceptions that happened in between the two calls would be picked up by the next call, else returned by the end. At least that's how I'm envisioning this implementation.
I'm not sure. You'd have to go digging in there, and I haven't. I must admit that I've not used this extensively in the wild, so I'm not an authority on it. But the good news is the source of mask is available in control exception, and then the underlying calls to the block and unblock functions are in ghc.io. So you could just totally like go and look and see how it works if it's something that interests you, which it probably should if you're going to use it. So this is a little extreme. I have talked to some people that are in this room that write a bit of Haskell, and I've been told that folks will oftentimes use the bracket function, which abstracts over what you're seeing in that earlier example. So as I mentioned before, control exception exports a bunch of functions that build on some of these lower level functions. Bracket, as you can see, you give it an IO computation, which would be like lease my connection from the pool. You give it some function that tells it how to release that connection from the pool. Speaking concretely about the prior example, and then some operation to you give it a function that expresses what you want to do with that connection, and then your resultant value is of type IOC. You run it, and then it does all those things. So you can sequence it in with all the rest of your IO computations. Okay, so takeaways from this talk. Haskell gives you these normal values. Gives you normal values like either and maybe to represent success and failure in a way that you would somewhat expect. You also have this exceptional value mechanism to signal for sort of like out of band errors, and you have this idea of catching and throwing like you do in other languages. It just takes on a slightly different form. A thing to remember is that evaluation order in this pure code is unspecified. So if you are expecting that an exception, on the left side of the plus is going to get raised instead of the right side of the plus, as we demonstrated, like Darby Dragons down that path. Tons of tools in control exception for dealing with exceptions. I highly recommend also taking a look at the errors package by Mr. Gonzalez that provides you with some interesting ways of catching exceptions, or basically, let's say you have an IO, like a type IOA, and you can get back like an either T EA or something like that. It basically it gives you a way to sort of hide the catching. Certainly push it farther down. Also, monad throw and monad catch are very interesting type classes. I didn't have enough time to put them into this presentation, but I highly recommend you check that stuff out. And if you love this stuff, come talk to me about a job, because we are hiring. that's all I got. Check out all these papers. Well, not all these papers. You don't have to read all these papers, but they're all pretty good. And then a bunch of very practical blog posts, and then some section of Simon Marlowe's Parallel and Concurrent Programming and Haskell book explain this stuff really well. You'll find if you go back through these slides that I'm borrowing heavily from all of these different examples. So if you want if you want to hear it from like the real deal, go and check this stuff out. So that's it. Thank you very much. You can ask questions. I'll try to answer, but I'm not an authority, although I may pretend to be from time to time. Yes?
On the last one where you were talking about brackets,
Yeah.
I think I understood that those are run conditionally. Like sometimes the first line runs, the second line doesn't run, the third line runs. And did you get that flavor from bracket?
Well, let's take a look at the types. Run first, run last, run in between, return the in-between result. My read of this code is that all of these are going to come into play. Like you're still going to release the resource. You're still going to run this like run last operation, this second guy here, regardless of whether an exception is going to be raised. And I think actually now that we're talking about this, so sorry, for the microphone purposes, the question was, and pardon me for summarizing, like do all of these guys come into play regardless of whether or not an exception is raised? Is that like the spirit of your question?
I was under the distinct impression that it ran conditionally, the intermediate pieces.
I don't believe that is the case. And Phil, you can correct me if I'm wrong. I believe that all of these things, like,
I think they all run.
yeah, I'm pretty sure they all run. I think what happens is like if an exception is raised, it's going to be rethrown, but this thing is going to guarantee you that your release the resource operation is going to complete. So they all are going to come into play.
Well, that kind of suggests that the line 3 won't necessarily run.
Line 3 is like what you actually want to do with the resource. So this is like, the first guy is like, get my resource. This guy here is like, using my resource, do some stuff with it, or produce a computation that when run will like, give you something. This guy here is like how to release the resource, and this is the result of all of these guys composed into one I/O computation. Does that make sense?
But what if an exception occurred before you were able to run the third line? Makes sense to just.
At what point in your program? At what point in your program are you asking? The question is, what happens if an exception is raised before? You mean as a result of doing one of these things?
Yeah.
I'm not sure if an exception handler is installed around that or that or that. I know that an exception handler is installed somewhere in here because I know for a fact that that the implementation of bracket will rethrow an exception if encountered. But I don't actually know if it's catching here and here or just here. You'd have to like go digging into the code to find out.
I've seen a mechanism that looks like this in Python, and what they wanted to do is if you bracket some operation between two other operations, then you want to say even if something goes wrong with that one, the one that preceded it and following it still happen.
Interesting. I mean, that sounds like spiritually similar to like what's going on here. Yeah. Cool. Well, yeah.
So there's an example with the if you put in a monad, then you have to do the two operations sequentially.
Mm-hmm.
So I'm wondering, I think there's a new applicative do extension coming out. So I'm wondering if that would be able to convert that to the applicative.
Yeah, that's a good question. The question was like, what is the impact? I'm summarizing. What is the impact of applicative do on the verbosity level of like the code that we write? And that's a good question. I actually don't know what applicative do. I'm not sure what the result of that is going to look like in software. I haven't looked at any of the examples, but if I had to wager a guess, I would say, yeah, it would probably alleviate some of that problem. But you'd still have to like think about applicative functors, and maybe you just can't be bothered to do that. Cool. Yeah, what's up, Devin?
So the last question about bracket releasing the resource, according to the source, this is bracket is thinly wrapped mask that applies the after the after thing, the resource releasing thing. It applies that in two different places. Before it applies that in the handler in mask, and then also after. So exactly.
It's probably doing this right here.
It's actually abstracting that structure exactly. So it actually does the exact same thing as that, except wrapped, because I guess it's a common enough idiom. So the code suggests that there it is.
Cool. Yeah, I mean, I learned a lot about how this stuff works just by digging through the source code of control.exception. I encourage you to do the same thing.
Surprisingly readable.
Yeah, quite legible. Yeah. Cool. Well, thank you very much. Come talk to me if you want a job. Exceptions that we see today in the language. And they provided some justifications for why exceptions as values isn't always like the way to go. One of the things they mentioned was code bloat. Let's say you've got these two functions, f of g, which are from string to maybe string. You'll notice here that if I want to combine their inner values, let's say using string concatenation, I have to do this like error propagation check, and propagate, check, and propagate. I can eliminate some of the boilerplate noise in my program by using the monad instance of maybe, but then I've just incurred this first this, then this. I've created a sequence when actually these two operations have nothing to do with each other, just the concatenation. So you can get rid of some of this stuff by using applicative, but if we had to write this code all the time, our lives might be kind of sad. Especially if you show this to somebody coming to the language fresh, I think there's a little bit of like a hurdle that they'd have to jump over conceptually. Okay, you also run into this issue with modularity, where you're attempting to compose functions that could fail with functions that cannot fail in the ways that that we're talking about here. For instance, summing. You got x plus y, and you got y div z. So we know that if you try to divide a number by 0, you're going to get a runtime. Okay, exceptions in Haskell, beginner's guide. The format of this presentation is kind of a two-pronged attack. It's a book report. It's my sort of summation of an imprecise, a semantics for imprecise exceptions in Haskell. Asynchronous exceptions in Haskell, and this other paper that Simon Marlowe wrote about another paper that Simon Marlowe wrote about an extensible hierarchy of types. So there's that. I'm going to give an overview of the control exception API, give you some ideas on how you can use it, and provide a little bit of show you the semantics for exceptions bolted on to Haskell that you encounter in GHC today. Okay, so as I mentioned, I'm going to explain the exception semantics in Haskell and GHC specifically. I'm going to show you how to use them in your program. Beginning Haskellers start with exceptions as values. And what I mean by that is we've got these types like maybe and either that we interact with that help us represent failure in the type system. So you're going to use something like lookup. You're going to have like a map with keys of type A and values of type B. You're going to define one of these things. You're going to look something up in it. And if you're successful, you're going to get back just string. And if you fail, then you've got this value that represents an exception. You're going to get a div by 0 error. So we say we demand safety, and we write our own function safediv that returns a value wrapped in one of these maybe types. So we say we do some pattern matching. We say if you give me a denominator 0, we're going to give you nothing, and if you give me something else, then I'm going to do the division. I'm going to wrap it up and adjust for you. But now you've got this issue where you want to compose something that returns a type. Something returns a value of type maybe int with this other thing that just speaks with ints. You introduce a little boilerplate here. Once again, you can go back to the world of like applicative, or you can lift the result of this x plus q, or sorry, you can lift this little guy here, the plus q, up into the sort of maybe context. But it's certainly a whole lot more code than that. And we wonder to ourselves, like, am I really going to be dividing by 0? Is it really worth the additional characters for this marginal marginal benefit of safety? So the other thing that they talk about in Semantics for Imprecise Exceptions, which is a spectacular paper and really helped me understand like how this stuff works in GHC. They bring up the point that it becomes very easy to accidentally make your lazy Haskell program strict when the type that represents failure. Either type you're also familiar with. Either decode is a function in ASON. It's going to allow us to go from a value of type byte string to either string A, where A is a type that instantiates from JSON. So this is going to be a thing that's going to allow you to decode a byte string into some type. For instance, you call either decode, you apply either decode to some string with 1, 2, 3 in there, and you say try to decode this to a list of integers, and you're successful, so you get back the right constructor with list 1, 2, 3 is your value. You try to apply either decode to the same argument, but you try to, or you tell it to produce you a list of booleans, and you get left representing failure. So the notion of success and failure is encoded in these types. And then you do things like you use head, and you apply head to an empty list, and you see some weird crap in GHCI that says exception. You go, what? And then you divide 10 by 0, and you see something that says exception. You go, what? And then you try to read a file off the disk, and you give it some bogus path, and you see an exception, and you go, oh my God, I didn't even know Haskell had an exception system. I thought this notion of functional purity would mean I would never have to deal with these out-of-band, this way to signal failure in a sort of out-of-band way. Okay, so I was digging into the papers that ultimately resulted in the incarnation of type. The return types of your functions are these values. The return type, you're using these types that represent success and failure. So we know that Haskell is a lazy programming language. So I got this choice function that I wrote. It takes a Boolean, takes two integers or expressions that are reducible to integer. And depending on the value of the first argument, true or false, we're going to give you back the left or the right argument. So you give me a true, I'm going to give you x. I'm going to ignore the y. If you give me false, then I'm going to give you the y. This property allows us to do things like this, where I call choice with true. True means that I'm going to pass along the left side of this, so the x, and the right-hand side, which, if it were evaluated to normal, if it were to evaluate all the way down to normal form, would result in a runtime exception, but we don't actually do anything with it, so we can write code like this and have it not fail. So let's say, like, what do we do in a world in which, like, what do we do in this world in which, like, we write safe div instead of using our unsafe div? As I showed you here, choice composes easily with div. X div y is going to give you an expression of type integer. Y div z is going to give you an expression of type integer. So we do bar true bar applied to true 1010. We get back 1. 5 div 0 is never actually evaluated. No big deal.